In this example, big F of x is equal to the definite integral from 1 to x of square root of t squared plus 3 dt. We are asked to evaluate big F of 1. To evaluate, we just plug in 1 for x. This gives the definite integral from 1 to 1 of the square root of t squared plus 3 dt. Notice here that the top and bottom number of this definite integral are the same number. Whenever this happens, the value of the definite integral is 0. That's just a fact you need to know. Now let's look at the same function big F of x. We are asked to find big F prime of x. In other words, we want the derivative of big F of x. This is a straightforward application of the Fundamental Theorem of Calculus Part 1. The only potentially tricky part is to be aware of the variables involved. Big F prime of x is a function of x, not t. The variable that we're plugging in here should be x. So the final answer would be big F prime of x is equal to square root of x squared plus 3. Now we consider the same function big F of x, but we are going to find big F double prime of x, the second derivative. Remember that the first derivative of big F of x was big F prime of x equals square root of x squared plus 3. We found this using the Fundamental Theorem of Calculus. To find F double prime of x, we just need to find the derivative of F prime of x. This is going to be a good review of the derivative process from Calculus 1. When we look at this square root, it's easier to rewrite the function using the 1/2 power as an exponent. Because this is an expression, we need to use chain rule to not just x inside these parentheses. We will need to use chain rule to find the derivative. We take the derivative of the outside, leaving the inside alone, then multiply it by the derivative of the inside. Do a bit of algebraic cleanup. The 1/2 and the 2 will cancel. So we can rewrite the negative 1/2 exponent as a square root in the denominator. So this is what a final answer might look like if we cleaned it up completely.